Well, now we're going to bring back the definition or the term Wronskian, which means something slightly different than it did back in chapter 4. And by stating a theorem, and then we'll do a real simple example applying it. Okay, theorem. This Li just stands for linearly independent solutions. Okay, so suppose we've got these solution vectors, x1 through xn, and we need to keep in mind what the solution is. It's a list of variables. It could just be x1, y1 if there are only 2 of them, or it could be x, y, z if there were 3. But to be generic here, more general, we're calling them x11, x21 down to xn1. And the final one would be xn, capital Xn would be little x1n, 2n, down to nn. And you can get the feel if you put them next to each other. It would be a nice matrix because the subscript defines the row and column that each element would be in. This would be the second row, first row 2, column 1. This would be row n, column n. Okay, so if this is our n solution vectors of the homogeneous system, x prime equals a to the x, then that set of vectors, x1 through xn, is linearly independent on some interval, if and only if the following is true. The Wronskian, which we use this terminology, which is the determinant of, and then you just put the vectors next side by side with each other, x1 to xn like this, take the determinant of it, and it's not equal to 0 for all t in the interval I. So it's worth noting here that the Wronskian is slightly different. Remember last time for the Wronskian we had a row 1 was a bunch of functions. Then we had to compute row 2, which was all their derivatives. And then row 3 would be the derivatives of row 2 and so on. This, we don't have to take any derivatives at all. We just take these given solutions, put them into matrix form, and take the determinant. Okay, and just as a note, if the Wronskian is not equal to 0 for one specific value of t in the interval I, then it will not be 0 for any of them in that entire interval. And that would make x1 through xn a linearly independent set of solutions, which we frequently refer to as an FSS, a fundamental set of solutions. Okay, so here's our example. We got 2 vectors with only 2 elements each. x1 is, if I multiply it through, this would be e to the t, negative e to the t. x2 would be 2e to the t, 6e to the t. And we're given that they are solutions of this differential equation. So all we're asked here is, are they a fundamental set of solutions on the entire real line? And all we're going to do is compute the Wronskian. The Wronskian is the determinant, and I just put x1 in this column, so I'm going to put x1 will just be e to the t, and then negative e to the t down that column, and then 2e to the t, 6e to the t. All we do is take the determinant, which for a 2 by 2 is very simple. It's just this diagonal product minus this diagonal product. So we would get 6e to the t times e to the t, and that would give us, what would that give us? E to the t times e to the t is e to the 2t. So 6e to the 2t minus this product. Oh, that's a negative here. So that's going to turn it into, well, I'll just write it down as negative 2e to the 2t. So when we add those together, and we are adding here, minus a negative, it'd be they're like terms, and we just get an 8e to the 2t, which is never, ever equal to 0. It doesn't matter what the value of t is. So, yes, x1, x2 is a fundamental set of solutions on the entire real line.